A steel cylindrical rod of length L, radius R is suspended by its end from the ceiling. Find the elastic deformation energy of the rod. And in second part, defined U in terms of tensile strain of the rod. So a rod is suspended from ceiling. Its length is L, radius is R. Consider a section at a distance x from free end. At this section, the force acting between these two parts will be equal to the weight of lower hanging part of the rod. If you consider this part of the rod, its weight is rho density into volume. Volume is x into area into g. So this is weight. And this weight is balanced by force being applied at this section by this upper part. So this force will be equal to rho A x g, and the stress at this section will be divided by area of the section. Now we know this formula that energy stored is half stress into strain into volume. This is energy stored in a given volume. So if we take a small part here of length dx, how much energy is stored in that part, that we are going to find. So that will be half stress at this section we have already found. This is rho xg. So half is stress. Strain is stress upon Young's modulus. This is strain into volume. So volume of this part is A dx. So the total energy stored in this full rod is the integration of this du. So it is simply integration from 0 to the total length L, and which on solving we get this result. Area can be written as pi r square. Change in length dx. If we consider our dx length here, so ds was original length. When it is suspended, then due to weight, the whole rod will elongate, and so will this dx part. So the change in length dx will be strain into dx. Obviously, strain is change in length upon length. Strain is a stress over Young's modulus into dx. So total change in length of rod is the integration of this quantity. So we finally have this expression as change in length. From here, simple to find delta L over L. And energy can be written in terms of delta L by L also. If we rearrange the terms, we finally have this expression. And if we compare this expression with the energy of spring, so that is half k into delta L square. So if you compare the two formula for energies, then this quantity, the bracket, this quantity in the bracket is equivalent k of this rod. So this rod will behave like a spring having this much of spring constant, equivalent spring constant. Okay.